The input to our system is a small signal from across the eyes, measuring between 0.1 to 1 millivolt. That signal is amplified by about 500 times through an instrumentation amp. We selected an amp that could amplify signals which are very close to zero on the negative side without actually requiring a negative supply voltage, thereby reducing the need to create two power supply lines. We then send it through a second order passive low pass filter. We should have included a high pass filter, but we thought not to do so as to be able to retain the eye position instead of just change in eye position. We then send it through another ×4 amplifier made out of a non-inverting op amp, and finally through a unity gain buffer made out of an active op amp. That signal then goes to the ADC, and it's sent from the MSP430 through an FTDI interface to be processed on a computer. We then have an actuator circuit consisting of a vibration motor. Now, vibration motors create a huge current spike when they run, and to prevent that from happening, we use a low pass filter from carefully selected values, as well as a capacitor in parallel to smooth out the noise. We control the vibration motor through PWM from the MSP430 and power it directly from the battery, as the MSP430 is not able to provide the current requirement of between 30 to 100 milliamps. We have two lithium-ion batteries, CR2032, in parallel. Each CR2032 is not able to provide sufficient current to power the vibration motor, and therefore two in parallel does the job. A Schottky in series with each one prevents self-charging, which the CR2032 do not like at all. We also have a Bluetooth in our schematic. However, it was not realized in our board as the part did not ship, but we made do with a wired FTDI communication with the computer. In terms of the board tracing, we use 8 mils for signals and 16 mils for power to be able to efficiently route our board. And we try to keep the input analog signal and signal processing away from the high current vibration motor to prevent interference to signal. We're currently on about a 1.2 inch by 3 inch board, and we hope to shrink this further by using smaller component sizes. We're currently on the 0603 component size scale, as that is it's easy to hand solder, and also most fab houses are comfortable with doing that size for assembly.
The software side of the EyeVibrator uses an MSP430 for data collection. However, all the processing is performed on a computer, like an ordinary laptop or perhaps an embedded system such as a BeagleBone. The MSP430 sets an internal timer to record at a rate of about 480 hertz, so that we can silence any 60 hertz noise if necessary. In practice, we found that this doesn't show up as much as we were afraid of. Then the MSP430 relays its information back to a host someplace else for processing over a UART. And when the computer decides that perhaps the EyeVibrator needs to vibrate, maybe somebody's not reading right now, it can send a signal right back over, which will cause the EyeVibrator itself to start vibrating. Similarly, there is a button on the EyeVibrator which can be pressed to specify that there's something special about a given observation. For instance, if you were trying to calibrate it, or maybe you just wanted to add some other functionality. Because the ADC reading is only 10 bits, this is encoded as bit 11 in the message that's sent back over the UART to the host computer.
So now here's how we're trying to understand if someone's reading or not. This is a typical electrooculogram signal when someone is reading. And what we see is that the person's reading from the left of the page to the right of the page across a line, and then he drops back down right to the next line, and then continues to read across that line. And this drop is the first thing that we're trying to detect in our bio algorithm. We do so by measuring the gradient and detecting when the gradient suits the gradient of this drop. We count how many gradients happen per unit time. With that, we were already able to attain a reasonable amount of accuracy from data that we collected from an industry grade industrial acquisition system for EOG. Now the second thing that we're trying to measure as well is the jittering as you move from word to word as you read. And that's these little bumps that you see here. We count how many of these jitters happen in between the large drops, and we see if that the ratio is a reasonable number, we can determine if the person is reading or not reading. Okay. And this is what someone's EOG signals might look like when he's watching a video. The person's eye goes from feature to feature on the screen as different things on the screen attract their attention. And this is easily distinguishable from the reading signal because we don't have those large drops with the intermittent jitters in between, which is what our algorithm is trying to detect.
So one of the challenges that we encounter is that we did not receive a Bluetooth module from DigiKey. So we were a little bit set back by some of the modifications we had to make to our board in order to support plain UART. That explains many of the wires you will see sticking out from all over it. However, we are still proud to say that we can do data acquisition, it's just wired. We have a Bluetooth library that should be usable for standard Bluetooth connections. Bluetooth low energy should be possible on the client side using an Adafruit library, and the Bluetooth operations on the MSP430 are conveniently abstracted in some source code that we will also provide.
One of the key challenges that we faced as we worked upon this project was that we're dealing with a very small biological signal in the order of 0.1 to 1 millivolt, and this is not forgetting the noise that comes with it. To deal with this, we have analog signal processing, including an amplifier followed by second order low pass filter and another amplifier and then a buffer. With all these chained in series and it being the first prototype of our board, it was hard to get everything working in place. And even now we had to cut traces and make a bypass past the last two amplifiers, which degraded signal quality a little bit, but got everything working in time. Another thing with the EOG signal is that it varies significantly from person to person, and it's not very well studied in the field of medicine as the EEG for the brain, or the EMG for muscles, or the EEG for a heart is. Therefore, what we're doing with this data collection is a lot of new things, and we're beginning to understand like DC offsets and how different speeds corresponds to different voltages.
As of 9:13 p.m., we do not have a real-time reading detection algorithm. Well, we have an algorithm, and it runs in MATLAB. It has not, as of yet, been ported to Python, so it does not run with the data collection library that we wrote. That's all right, though. We're impressed with its performance in MATLAB, and we hope to change that quite soon.
One of probably the biggest challenge that we faced was the MSP430 breaking down. In our first board iteration, we believed that perhaps due to ESD, which is electrostatic discharge, or due to a misconfiguration of the ADC, we might have broken the MSP430, which took us a while to figure out. Once we were able to figure that out, we had to replace it using a heat gun, which we believe might have fried a second MSP430. But we finally got a third one in place and working, and refined our soldering skills a little bit. It was a good thing to keep in mind for future projects that the MSP430 can indeed break.